Good morning, colleagues and esteemed scientists. If you're interested in breakthrough research in electrochemical phenomena and newest enabling technologies, this is the webinar for you. Welcome to the Bruker Nanosurfaces webinar, titled Nanoelectrics at the Electrified Solid-Liquid Interfaces, in Operando Surface Potential Sensing of Photo-electrochemical Anodes. This joint webinar, co-hosted by Mike Nellist at the University of Oregon and Teddy Huang at Bruker AFM, will cover both the latest solar wafer splitting research in Boettcher group at the University of Oregon and Bruker's recent Nanoelectrode probe and data cube developments. During the webinar, I encourage you to use the questions window on the webinar user interface to submit your questions for discussion at the Q&A session after the talk from both Mike and Teddy. The recording and presentation material from this webinar will be made available to you in the coming days through a follow-up email. I also encourage you to fill out the survey at the end of the webinar to help us improve our webinar sessions. My name is Hector Lara, Product Line Manager of the Dimension Scanning Probe Microscopy products at Bruker AFM. Dr. Michael Nellist just finished his thesis defense from Professor Shannon Boettcher's lab at the University of Oregon on Tuesday. Congratulations, Dr. Nellist. His graduate work has been focused on better understanding of the charge transfer processes that take place at the semiconductor catalyst interface at photoanodes for water splitting. Michael earned his BS in chemistry from SUNY Geneseo. Dr. Huang is a staff application scientist at Bruker AFM unit. He obtained his PhD degree in physical chemistry from Emory University in 2012. After graduation, he worked for Professor Nathan Lewis at Caltech as a postdoctoral scholar, where he investigated the semiconductor metal interface structure using AFM nanoelectric measurements. He joined Bruker in 2014 and now leads a team for development of AFM-based electrical and electrochemical applications. As of today, he has published 43 peer-reviewed articles with more than 2,400 citations and a Herfindahl index of 22. Now, without further delay, I hand off the microphone to Dr. Nellist.
Hi, thank you, Hector, and thank you, Bruker, for allowing me to share my research with you today, and thank you all for being here in attendance. Today I'll be talking to you about the work that I've done over the last few years, developing in operando potential sensing techniques to look at photoanodes for water oxidation, and doing so using Nanoelectrode AFM probes. Really quick, the motivation that our lab has for studying these systems comes from thinking about how we currently obtain our power and energy and how we're going to get it into the future. So currently we use around 17 terawatts, most of this coming from fossil fuel-based resources. But it's expected by 2050 we're going to need 28 terawatts. It goes without saying that we should not only be working to reduce our dependence on fossil fuels now, but as we add new power generation online, fill that gap with cleaner energy sources, such as solar energy. Solar is a really attractive form to use our energy, or get our energy from, because it provides 120,000 terawatts of power continuously hitting the Earth. So we really only need to capture a very small portion of the sun's radiance on the Earth in order to power society well into the future. What's even more promising is that solar is starting to become cost competitive with traditional fossil fuel-based resources. So it seems like most of our problems are pretty much solved, except for the fact that energy resources like solar are intermittent. So the sun goes down, but we still need to be able to use energy in our homes, and we need ways to store that energy for those periods of time. If we think about how we currently get energy, well, fossil fuels have energy storage built into them within their chemical bonds, which makes them really advantageous for ease of use. But we can't shine sun on materials and make gasoline, so we need to have creative alternative ways to do so. Lithium-ion batteries is an emerging technology that has advanced significantly over the last couple of years. And here, this shows a solar field that's charging grid-scale batteries that help to stabilize the grid and store energy for times that we need it and the sun isn't shining. However, overall, lithium-ion batteries have relatively low energy densities. At less than 1 megajoule per kilogram, it requires significantly more materials to store the same amount of energy. Because of this, we might need alternative technologies to store our excess energy as well. And this is where hydrogen fuel as a potential energy storage system becomes really advantageous. At 145 megajoules per kilogram, it's significantly more energy dense than batteries or even gasoline. And with that high energy density, it makes it easy to use for fueling large devices such as cars, planes, and trains. And that's an actual hydrogen-powered car that's in production. At the bottom, that's an actual hydrogen-powered train that runs in Germany. Unfortunately, most of the hydrogen that we generate now comes from a process called steam reformation that relies on fossil fuels to produce the hydrogen. So if we're going to scale our hydrogen usage to much larger amounts, we need ways that we can generate that hydrogen from clean resources. For example, just sun and some water. And that's the idea behind photo-electrochemical water splitting or solar water splitting, where we can shine light and split water into oxygen and hydrogen. There's two main components. There's the photocathode that's responsible for reducing water and generating hydrogen, and the photoanode that's responsible for oxidizing water and evolving oxygen. These two half reactions need to take place simultaneously in order to drive the solar water splitting of the complete system. If you look at the components separately, though, well, it turns out that the water oxidation reaction is the kinetically slow process of the two. Because of this limits the efficiencies of these overall photoelectrochemical water splitting devices. So if we want to improve the efficiencies enough that we can allow these devices to see the light of day, it's important that we understand this photoanode and the water oxidation processes that take place at it, so that we can make steps to improve the overall kinetics and lower the potentials required to drive that water oxidation. So if we zoom in on the photoanode, there's the semiconductor that's responsible for absorbing light from the sun. And there's a catalyst that improves the kinetics for the water oxidation and reduces the potentials needed. And then the solution that we drive water oxidation from. So the simple picture here is the sun will shine on the semiconductor, and that will generate an electron-hole pair. And that hole can make its way to the semiconductor catalyst interface where water oxidation is driven. However, this simple picture isn't really representative of what the field generally understands about how these systems work. And really, there's a significant question that has lingered about how exactly these catalyst overlayers improve the kinetics for water oxidation. This is really well exemplified by comparing a number of different studies that were done looking at cobalt oxyhydroxide phosphate, or CoPi catalyst, coated on hematite or iron oxide semiconductors. To give you an example of this, some groups have used photocurrent and impedance analysis to study these systems, and have found that the photo-generated holes from this hematite semiconductor get transferred to the CoPi catalyst, and that oxidizes cobalt in that catalyst from the 3+ to the 4+ state, and then that catalyst directly drives water oxidation itself. Conversely, other groups have used transient absorption or intensity modulated photocurrent spectroscopy, and their data suggests a very different picture. Instead, they observed the photogenerated hole in the semiconductor transferring to the semiconductor catalyst interface, and then staying at the surface of the semiconductor long enough to drive water oxidation directly at that surface. This is possible because catalysts like CoPi are highly porous, so the solution could permeate in through the catalyst and reach the semiconductor surface. Lastly, other groups have used more traditional photoelectrochemical and impedance techniques, and have found or have hypothesized kind of a hybrid approach between these two, where depending on how thick the CoPi layer is, some of the water oxidation may take place within the catalyst itself, and some of it will take place at the surface of the semiconductor. Overall, these different groups have used very different techniques studying the same systems and had very different hypotheses for what are going on. But one thing that all of these groups and the techniques have in common is that they're using bulk-type measurements to try to say something about the catalyst layer in isolation. if we really want to understand what the catalyst layer is doing, it's important that we develop a technique that allows for the direct measurement of the catalyst electronics independent of the semiconductor itself. We were trying to brainstorm ways that we could do this, and one potential idea that we had was using an AFM setup, electrochemical AFM setup, that uses a conductive AFM probe to measure the catalyst electronics separate from the substrate. So the idea here is pretty simple. We have our first working electrode attached to some substrate that's either conducting or semiconducting, and we can illuminate that substrate. We can electrodeposit a catalyst on the surface, and we can still build in our reference electrode and platinum counter electrode. What's unique here is now we take a conductive AFM probe, place it in the electrolyte, and we can scan the catalyst surface and pick a region to probe the electronics of separately. The challenge, though, is that if we put a conductive AFM probe into the solution, we run the risk of having parasitic reactions taking place throughout the conductive region of the probe. Likewise, because we're working in electrolyte, it's also possible that ions from the electrolyte will form capacitive layers across the conductive regions of the probe. And in both cases, this would disrupt the very sensitive nanoscale electrical measurements that we need to make. So to get around this, we could do something kind of clever and take these conductive probes and fully insulate them with some kind of insulating material like silicon nitride and leave the exposed conductive tip uninsulated. That way we know that when we bring the probe into contact with the catalyst, only that exposed tip is what's actually making the electrical measurements of interest. This is, of course, possible with the SECM probes that have been developed by Bruker, and it turned out these probes were ideal for these dual working electrode measurements that we want to develop, as shown here. So again, this is our setup. We have our first working electrode that's attached to the substrate, and our second working electrode, which are these fully insulated nanoelectrode probes with an exposed conductive tip. Both the first and the second working electrode are going to be referenced to a common reference electrode, and then we'll have our current counter electrode to allow the current to pass through the system. We're essentially going to, throughout the experiments, apply a potential to the substrate, and then measure the corresponding potential of the catalyst at the surface. However, we first needed to make some alterations to our electrochemical cell, and that is shown here. And so the top half of the electrochemical cell, this is what came with our Bruker Icon instrument. And we made modifications with this by adding this Teflon base plate to the bottom. This allowed two different things to happen. First, we could build in a port to allow for a real reference electrode. And second, it allowed us to place our samples over an illumination hole so that we could put a light source underneath the sample and illuminate our semiconductor materials from the bottom. You can kind of see with this hematite sample that's currently mounted on the Teflon base plate that there's a hole underneath where our light source will go. With our electrochemical cell set up, we could then go and try to put this on our AFM. A typical Bruker Icon AFM looks something like this, but you'll notice that the distance between the scanner and the bottom of the stage is rather small. This won't allow for our illumination setup. So instead, when we were ordering our AFM through Bruker, we worked with them to custom design our system so that the scanner and the stage are essentially put on stilts and lifted about 7 inches. We could then take this whole stage structure and take that off and replace it with an optical stage that looks something like this. We can then put a sample holder in our electrochemical cell on this illumination stage, and then place some kind of illumination source underneath. Here, this is the 405 nanometer light source that we'll be using for the experiments that I showed today. So now with our complete AFM setup in place, we wanted to see if we could use these nanoelectrode AFM probes to sense surface potentials. We wanted to test this on the simplest system possible, so we simply took a gold-coated glass slide, made our first working electrode contact to that gold slide, and brought our second working electrode into contact with that gold as well. We then used the first working electrode to step the potential of the gold anodically over time, while using our second working electrode to measure the corresponding surface potential of the gold. That's shown here, where the gold potential is in black and the potential of the gold measured from the tip is in red. And not surprisingly, we exactly measure the potential that we're applying to the first working electrode using the second working electrode. Gold, of course, is very conductive, so we wouldn't expect to see any kind of potential loss across that film. So this works for the simplest system that we could think of. The next most complicated system would be taking that CoPi catalyst that we're interested in studying and depositing it on some conductive substrate and repeating this measurement. So that's what we did. This time we're using ITO, or indium doped tin oxide, and made our first working electrode contact to that. We then electrodeposited about 100 nanometers of CoPi on the surface. To test the bulk electrochemistry properties, we ran a cyclic voltammogram, as shown here, where we start at low applied potentials, and as we slowly increase the potential, one feature that you will notice in our cyclic voltammogram is this oxidation wave that corresponds to the cobalt hydroxide in our CoPi catalyst being oxidized to cobalt oxyhydroxide. After this oxidation wave, there's this region of exponential current growth, and this corresponds to the onset of the oxygen evolution reaction. As we scan back, we get another wave that corresponds to the cobalt hydroxide, or the active form of the catalyst, being reduced back to cobalt oxyhydroxide being reduced back to cobalt hydroxide. And in all of our experiments are going to be referenced to the thermodynamic redox potential for oxygen evolution. So with this simple bulk measurement that's using just our first working electrode, we confirmed that our CoPi catalyst was in fact catalyzing the water oxidation reaction on a conductive substrate. And we went ahead and repeated that potential stepping experiment by taking our Nanoelectrode probe, immersing it in our electrolyte, scanning over the surface of the CoPi, picking a location that we wanted to probe individually, and applying a 25 nanonewton force via the probe onto the CoPi surface. We determined that 25 nanonewtons was about the amount of force that we needed to ensure that we maintained good electrical contact over the course of the experiment, but not too much force that resulted in the catalyst being destroyed or disrupted. We then step the potential like we did in the case of the gold electrode. We see something a little bit different here. We're at low applied potentials to the conductive ITO substrate. The potential measured at the surface of the catalyst via the tip does not track well. But once we get to about 0.3 volts, the potential that we're measuring via the tip starts to equilibrate to what we're applying to the ITO. And for the remainder of the experiment, those two potentials track very closely. While this looks very different than the gold case, this actually makes sense for the CoPi catalyst itself. Because CoPi starts off as cobalt hydroxide, which is an insulating material, it needs to oxidize to cobalt oxyhydroxide. When it's in its insulating state, the probe can't sense the potential because it's too insulative. But once it's conductive, it can measure the potential that is of the CoPi that's equilibrated to the ITO. We can take this raw data and plot it in a little bit more meaningful way by taking the potentials at the end of the potential measured via the tip of the catalyst at the end of each time step and comparing it to the potential that's being applied to the first working electrode. And that's shown here in orange. So again, at low applied substrate potentials, there's very little reaction to the catalyst potential until we get to just shy of 0.3 volts. And then we have this nice linear response in the measured potential. In the background, we have a CV corresponding to the left current axis. So we've now shown that we can sense surface potentials of cobalt or CoPi catalysts on conductive substrates. Now this was kind of the moment of truth for this technique. Can we place this catalyst on an illuminated hematite semiconductor system and repeat this measurement for the case that our holes that are being transferred to the catalyst are coming from a photo-generated source? So we took a sample of our iron oxide or hematite, and we photo-electrode deposited about 100 nanometers of CoPi on the surface. Again, we used our AFM probe to raster the surface and find a region that had nice catalyst coverage, and then applied 25 nanonewtons force while we do these potential stepping experiments. Like we saw before, at low applied potentials, while the hematite is illuminated, there's very little change in the measured potential via the tip until we get to about negative 0.4 volts, where there's this large step function that takes place in the measured potential, and then slow increases in the measured potential from there. This was a really exciting result because this directly demonstrates that this CoPi catalyst is accepting the photogenerated holes from the hematite, and the catalyst itself is in fact oxidizing. But what this measurement doesn't tell us yet is if the catalyst is directly responsible for driving the oxygen evolution, or if that oxygen evolution is still taking place at the semiconductor surface. So if we want to answer this question, we have to kind of go back to our measurement and think about it in a little bit different way. And so to do so, I'm going to start off with our control experiment again, where we use a conductive ITO substrate coated with the CoPi catalyst. In this case, we're going to compare over the experiment the potential that the catalyst is at, as measured via the tip, to the current that is passing through the system as a whole. I like to think of the current that passes through the system as a measure of how much water oxidation or how much oxygen bubbles we have evolving from the surface. And the catalyst potential is a measure of how many holes or the density of holes that are building up in the catalyst itself. So at low catalyst potentials, we don't have too many holes in the catalyst or too much water oxidation taking place in the solution. But as the catalyst potential starts to build, we get more holes in the catalyst, and we may start getting some water oxidation taking place in the solution, and more holes equals essentially more water oxidation. And this is pretty consistent with how we think of these catalysts working on conductive substrates. And so the question now is, if we take this CoPi and put it on a photoanode substrate like hematite, will it behave mechanistically similar? And so we repeated this for CoPi-coated hematite and plotted it together with the CoPi on ITO situation. And interestingly, these two curves superimpose on each other. And this tells us something very important, and that's that the same number of holes need to build up in the catalyst to drive the same amount of water oxidation. Again, because we know ITO is a bad material for driving water oxidation, we have a general understanding that holes need to transfer to the CoPi catalyst for that, and the CoPi oxidizes to the 4+ state and then directly drives water oxidation. So because these two curves superimpose, we now know that CoPi is accepting holes from the substrate and directly driving water oxidation in the situation where we have CoPi-coated hematite electrodes. If we go back to the initial controversy for how these systems work, well, our measurement now definitively proves that it is in fact this first case where the CoPi catalyst needs to be oxidized. So that's the situation for CoPi on a hematite photoanode. But since those initial studies came out, there's been a number of groups that have debated the role of CoPi catalyst on bismuth-vanadate photoanodes. One of their arguments for the difference is that bismuth-vanadate has faster kinetics for water oxidation, therefore is more likely to drive the water oxidation directly, even with CoPi deposited on the surface. Our question then was, can we apply our potential sensing AFM system that I've just shown you to the system and determine whether, in fact, the CoPi is driving the water oxidation or the bismuth-vanadate? And if the bismuth-vanadate does have different kinetics or faster kinetics, will this change the mechanism for water oxidation as well? So I started off with some bare bismuth-vanadate films and ran them in under illumination as well as in the dark to test their photo-electrochemical properties. I then deposited a very thin layer of CoPi on the surface and saw a dramatic improvement in the photocurrent onset and photocurrent throughout the duration of the cyclic voltammogram. This was really exciting. This seemed to be working really well. I then went ahead and deposited the additional catalyst that I needed to implement the dual working electrode AFM, or the potential sensing AFM technique, which is about 100 nanometers of catalyst on the surface. When I did this, all of my photoactivity and photocurrent for most of the CV disappeared. And in fact, the activity of the device was worse than without the catalyst at all. This was a little concerning, and we weren't really sure exactly what was going on, so we started some materials characterization, like doing scanning electron microscopy. And what we quickly realized is that these bismuth vanadate films are actually quite thin, less than 50 nanometers throughout the surface. So this could have a really profound impact on the catalyst loading if we think about these bismuth vanadate grains being too small to have grown together. So here you can see that the grains are separated, and this results in exposed FTO to the electrolyte. So if we go to really high CoPi loadings, like I just showed you, well, that could lead to CoPi depositing both on the bismuth vanadate, but also coming in contact with that conductive FTO substrate. So our picture of what we think was happening here it goes something like this, where photogenerated holes are transferred to the CoPi catalyst, and that CoPi is oxidized from cobalt hydroxide to cobalt oxyhydroxide, which is conductive. And now we have a direct pathway between the bismuth vanadate and the FTO for the photogenerated holes that transfer to directly recombine with electrons in the FTO. And we call this shunting recombination. This is especially possible because bismuth vanadate has a really high photovoltage, over 1 volt. And so the potential of the catalyst near the bismuth vanadate is going to want to sit a full volt higher than the catalyst that's in contact with the FTO itself. So this explains our poor activity from our high CoPi loading, but can we use this mechanism to explain why we have good activity for low loadings of CoPi? Well, we think this makes sense too, because when you have really low CoPi loadings, the CoPi catalyst on the surface of the bismuth vanadate is not completely connected. And so any regions that are in contact with both the bismuth vanadate and the FTO will only shunt that local catalyst region and not the entire catalyst film. We wanted to confirm this mechanism, so we took our thin bismuth vanadate films, made cross-sections using FIB, and ran TEM images to look at the cross-sections. And sure enough, we saw regions throughout the cross-sections where pinholes were in fact present in the bismuth vanadate films that left the FTO substrate completely exposed. So with this potential mechanism, with proof for this potential mechanism, we wanted to think of ways that we try to get around this. And one idea that we had is simply making the bismuth vanadate films thicker to hopefully reduce pinholes. And the idea here is that either the grains would be able to grow larger, or new grains would grow on top of the grains, effectively blocking all pinholes in the film. So I developed a new spin coating procedure to make bismuth vanadate that used more concentrated precursors, and then 10 total cycles to ensure that all of the pinholes were filled. We then again ran FIB and TEM to confirm that these films were pinhole free. And sure enough, there were no regions where pinholes originated from the surface of the bismuth vanadate and made it all the way down to the surface of the FTO. And while there were significant holes and porosity in the bismuth vanadate film itself, the important thing to note is that at no region was the FTO exposed from the surface of the sample. So with this sample in hand, we could then repeat our CoPi loading experiments. And this time, with additional CoPi loading, we had better photoactivity. And this makes sense because with more catalyst, we should be able to drive more water oxidation. Most importantly, though, we now had our model system that had non-shunted catalyst and a catalyst that was of sufficient thickness that we could employ our dual working electrode AFM technique. So like I did with the experiments for CoPi and hematite, we started off with potential stepping of the first working electrode while illuminating the bismuth vanadate and measuring the potential via the second working electrode. And at low applied potentials, there's very little response until we get to about negative 0.75, where there's a large step function taking place that corresponds to the COPI conductivity turning on, or holes building up in the COPI catalyst. From that point, we get small increases in the resulting measured potential of the catalyst. We ran our control system looking at COPI on conductive FTO substrate, and all of this data looked consistent with what we'd seen before. And then lastly, to understand how much water oxidation the COPI was directly responsible for driving, we compared the catalyst potentials to the current being driven through the system at the same time, like we did before. And sure enough, when the catalyst is in its conductive state, the lines superimposed for the COPI on FTO and the COPI on bismuth-vanadate. So regardless of what substrate our COPI is on, it is being oxidized to sufficiently high potentials to drive all of the water oxidation. The impacts of this work are numerous. First, we developed a technique that allows us to use these nanoelectrode probes to measure surface potentials and use that to measure surface potentials of metal oxide oxygen evolution reaction catalysts. We also demonstrated that COPI acts as a hole collector on both conductive and semiconductive substrates, and that is the primary source of water oxidation taking place for ITO or FTO conductive substrates and hematite and bismuth-vanadate metal oxide semiconductors. Really quick, I'd like to thank I guess everyone in my lab and the people that I've worked most closely with, my advisor, Dr. Shannon Boettcher, and all of the collaborators that have made this work possible. Thank you for listening. I think at this point I will transfer the presentation over to Dr. Teddy Huang, who will be taking over the next portion of the webinar.
Good morning, everyone. So on this section, in the next 15-20 minutes, I'm going to show you some new application that recently developed in Bruker, and of course, this is a lot of collaboration ongoing here, and then I'm going to show you a lot of unpublished results. So, and this section is focused on nanoelectrical scanning probe microscopy in liquids. And I will talk about some general feature that Bruker have for nanoelectrical measurement, and then I move to the liquids, including both the non-polar and the polar liquids. Bruker has provided a versatile array of nanoelectrical technique for a lot of applications. I mean, showing here is a quick example. So pretty much whatever you can measure in the bulk, you can just use the AFM tip, and then together with the sample, build a electrical component and use your sensor circuit to analyze the electrical signals. And this technique including surface potential, which is bias, which is voltage, or you can do conductivity resistivity measurement, which is current, or you can do charge, like carrier density, like capacitance, and then SSRM as microwave impedance. And you can measure electric field, piezoelectric impedance itself. So it's really very colorful applications here. And of course, you can integrate with other functions like photoconductive, AFM. And Bruker has its unique fundamental AFM modes. For those who has used our recent product should have already known about that, which is called peak force tapping AFM technique. So combined with this peak force tapping technique, we extend our nanoelectrical capability to a lot of other applications. So first, let's take a look at what is the peak force tapping. It is of resonance tapping mode, and the tip is drive with a sinusoidal voltage, which actually has a sinusoidal movement. And with this sinusoidal driving, that when the tip approaching the surface, it has a soft turning point. And with this soft turning point, you can have a very good control on the tip sample imaging force or the peak force. And with this fundamental features behind, I mean, you can use a very low force to do the imaging. And because this is of resonance tapping mode, you don't need to worry about the cantilever tuning, which is very handy for a lot of tricky sample surface, especially for environmental control at different ambience. And of course, because it's tapping mode, you don't need to worry about the tip wear, the shear force that like inherent to a lot of contact mode based imaging mode. And with this, combined with the nanoelectrical measurement, and then for a lot of previously AFM inaccessible dedicated sample, you can measure them. And of course, because for every tapping cycle, we get a full cycle of the force distance curve, and based on that, you can also get a quantitative nanomechanical data. And just keep it short, pretty much the peak for nanoelectrical measurement has a lot of advantages, and then 3 of them are listed here. First, improve the tip lifetime with hard sample, and then decrease the sample wear with soft sample. And because this is gentle force, it also improves the resolution due to the sharper tip and less sample damages. And this is a very famous example, and published in Nanoscale in 2012. And this is actually some P3HT lamina polymer, and then with the carbon nanotube backbone. You can so with this technique, you can do the topography imaging, has no problem, and then at the same time you can also measure the conductivity current, and you can also from the adhesion map to differentiate different material. And for this sample, it's very, very challenging for any other mode. For contact mode, a tapping mode is not possible to measure the current. And we recently released a new mode called Data Q. So Data Q nanoelectrical mode, and these modes are based on the Bruker unique force volume technique. So force volume imaging is actually based on taking the force distance spectrum in every pixel. It's similar to the peak for tapping. However, the ramping, the G ramping mechanism is a little bit different. So for Data Q, it take the advantages of the force volume, and it actually insert a segment called hold segment or dwell time. And then when you put the tip holding on the surface, during this holding, you can perform an electrical measurement. For example, electrical spectrum. And then if you do it on every pixel, then you are going to have an electrical spectrum in every pixel. And what kind of electrical spectra that we can have? And this spectra including, for example, IV curve, capacitance versus sample bias, or PFM switching polarization change. You can do like a surface spreading resistance microscopies. You just run the bias to get the resistance value. Or you can do DCDV versus the sample bias, the contact resonant PFM, like PFM versus frequency. So it's actually more than this. And imagine that now you have you have on every pixel you have a spectrum. So you essentially like getting a very high dimensional data. And then, for example, the data we get, for example, this is example PFM phase versus the sample bias you apply. You can see that right on the vertical, on the every horizontal plane is actually is PFM phase distribution on the specific sample bias. But on the vertical plane, you can see that this is actually the phase change, because the vertical direction here is the bias. Is the phase transition along the bias. You can see that different switching bias happen at different location of the sample bias. And of course, because this is essentially a hopping mode, like similar to the resonance tapping in the peak fault tapping, so you also retain other advantages of the peak fault nanoelectrics. So Dr. Peter de Wolf from Bruker, he gave a webinar not long ago. If you're interested in more detail about this mode, you can go take a look. And today, I'm going to cover a little bit about Data Q for nanoelectrical measurement in liquid. So nanoelectrical SPM in non-power liquids actually has a lot of advantages. So for example, you can use some oil or wax that people would use, right, to cover the surface, and which actually you can clean the surface. You can mimic in a vacuum for some fundamental study for more quantitative analysis. And doing measurement in liquid has another advantages for AFM imaging, which you're free from the capillary force, and then you can perform low force imaging, which of course will increase your resolution, preserve your tip better. And for non-polar liquids, it's actually you just change the dielectric environment, like a best similar to air. Now you just put something that like another type of dielectric material. So for this kind of measurement, because it's not conductive, and then it's not polarized, and then normally you don't need a special probe. So example back in 2012 is actually this group they try to study the cell, the alkene cell on the cell assembled monolayer, and how this attach, how this absorb, how this SAMs that can tune the work function of the underlying metals. Of course, use the SAM to tune the work function of the metal is very attractive to optoelectronic devices. So for this kind of like devices, if you want to know the surface work function, or if you want to measure the contact potential difference, the CPD, reliably, you definitely need a clean surface. So normally people would like to do it in the ultra high vacuum, and I just mentioned the other way, right? You can do it in liquid, and then compare to the ultra high vacuum technique. KPFM in non-polar liquid is actually much less technical demanding. It's very easy to run some measurement in liquid as long as it has the hardware ready, and then that's commercialized already. And as you can see that, right? So this is the sample prepared from nanospeed lithography, and they have the gold and the silicon dioxide. And actually, they use the silicon dioxide as internal references and do the measurement. You can see it's a well differentiate the different domain. And then they also compare the surface work function shift that when they add the the cancyl molecule layer on the top of that, and you can see that they can compare different shift. And this is actually quite I think I remember the paper said that it's quite reliable and then quite repeatable. And I think the most important thing, if you take a look at this shift here from air to that in the decant with the HTD coding, they also compare the result that they get and analyze and then from the UPS, and this is very consistent with the high vacuum with the UPS measurement here. So this is the advantage of this technique, which of course is much less technical demanding. And we also try some PFM in non-polar liquids. Of course, as I mentioned, right, non-polar liquid can give you some high resolution measurement, and you don't need to use some special probe. And here we just use a regular Bruker SCM PIT probe. And as you can see here, this is a PPLN sample, which is very familiar for who running PFM studies. And you can see that the topography, you won't see any contrast, but this is actually an area that has two faces here, two different domains here. And if you take a look at the transition or the thickness of the domain wall, you can see that it's actually about 10 nanometer, and pretty much the resolution is only limited by the tip by the end tip radius. And of course, people would like to use a contact resonant PFM to enhance their signal. So if you dry your piezoelectric material near or coincide with the contact resonance, and then the signal can be enhanced according to your Q factor of your probe. And so this is a very popular technique. However, for different domain, because of different electrical surface charge or some other reason or different mechanical properties, and then the contact resonance response for different domains is going to be different. So if you just want a single frequency measurement, that's not going to be sufficient for getting out the accurate, for example, contact resonance amplitude or contact resonance phase. So with the DQ, you can perform a frequency sweep on every inlet pixel. Then you can offline, for offline analysis, you can do a very good resonance tracking, and of course you can get both the amplitude map and also very important, you can get a phase at the contact resonance, and this is very robust to differentiate the domain of different polarization. So with DQ, as I mentioned, this is actually a technique because you actually get a spectrum on every pixel, and by that you can obtain the high volume, high throughput data. For example, I'm showing here on this slide in the back. is 206 PFM amplitude images. And imagine that I can do 4 channels simultaneously, phase, amplitude, diffraction, height sensor. In total, I have more than 1,000 images. And if you and this is actually from I think this is actually from, let me take a look, from 75 to 250 kilohertz, and for the spectral resolution, it's like less than 1 kilohertz per images. And this image is actually highly correlated. For example, when you capture that, this is actually a time series data. And then you have a multiple channel, and they're also correlated. So you have like correlated data cube. And because DQ is based on force volume, you have a force distance curve cycle on every pixel. Then you can also get all the quantitative nanomechanical information. So this is a very information-rich technique. Of course, I'm saying that this is 260 images. I can easily make 1,000 and give you higher spectral resolution as needed. This is one of the data visualization example. So I'm showing here it's just the PFM amplitude channel of the PFM amplitude cube. And now you can with the slices that you extracted. You can make the movie that's showing the image along 3 different directions. For example, along the frequency direction that you can look at the dynamic electromechanical property that when changing the frequency, or spatially how the PFM response that change along, for example, X direction or Y direction. And of course, you can also create a visualization of the data cube. And for different channels, you can also make them together and then see the correlation. For example, this is a movie that's showing the 2 of the channels that are changing with the frequency. And this on the below the at the bottom of the movie here, I'm showing the typical spectrum of the 2 typical domains. And you can see that the simultaneous change of the phase and the amplitude. And now with such a high volume, high density data, now you can introduce the statistic to do the analysis. For example, the density plot, a very popular technique that show the most common presented features. And in here, of course, 2 distinct PFM domains are differentiated by the two type of density plot in either the phase or the amplitude channels. And again, with such a high volume data, now you can start to talk about quantitative analysis. For example, because inherited from the contact resonance, you can get all the contact resonance result. And this just show some example here, like a contact resonance amplitude frequency. You have tons of them as shown here. And also you can, based on the classic force distance curve, you can get an adhesion map, modulus map, and more than that. And just another example for the data mining is as I mentioned, right? Because if you want to compare the contact resonance phase to differentiate 2 different domains, you have to compare them when they add resonance. And it's very easy to extract this kind of information and plot them into the map. And you can also do some statistical analysis. For example, for this sample, you can see that they have a phase difference histogram like this. You can also see the transition here. Okay, so actually for non-polar liquids, nanoelectrical measurement is actually much less challenging for polar liquids, but the real application is actually more important for polar liquid because this is related to the practical application, including like energy research, like lithium-ion battery, as you can show here. For example, how the SEI layer formation is going to affect the electrical conductivity. You want to do the conductivity measurement in the polar liquid in a battery solution. And like for example, like a human body, is a very good electromechanical system. You have electrical pulse to change your muscle movement, change the volume, and on the other way, when your muscle contract or extend, it will generate some electrical signal. So you want to study electromechanical like PFM in liquid, and then you have a thing that Mike just showed you a very good example how to measure the surface potential in our planar electrochemical system. There's actually another very important property that electrochemists would be very interested in is the interfacial conductivity when you put two components like catalyst onto a semiconductor substrate as an example. So there's a lot of interest in this area that running electrical measurement in power liquid, in electrolyte. So of course, it has a lot of challenges. Mike already mentioned some of them for his surface potential measurement, and of course, from the view of the product, of course, you need to make something that can compatible with your environment or your chemicals. And Mike just mentioned that you need to also worry about the persistent electrochemical reaction, the straight capacitance due to the bare metal electrode. And another challenging is about the resolution, because if you are in a conductive liquid environment, if you use a non-insulated tape, you are going to have a delocalized electric field, and then you will lose your resolution. So it's better that you would like to insulate the probe. And with this, the solution provided by Bruker recently, that of course we use isolated leakage-free nanoelectrode, and that Mike just showed you, and for the chemical compatibility and the environment for do this measurement, we have optimized special tip holder and also the container, and we pretty much after we solve the problem about this kind of like spill-free, leakage-free. And then now we can implant all the nanoelectrical mode in air, transfer them to liquid. And this electrical mode in air has been well tested, has high performance and then high bandwidth. So now we just take them to do the liquid measurement. And one example is a collaboration with Professor Zhigao Hu in China, in East China Normal University, and they are interested in the PFM biomimetic environment. So normally, for example, as a human body, right, our body has a liquid like 100 millimole, like sodium chloride, potassium chloride in your body, and it has a pH, has a neutral pH. So if you want to apply your ferroelectric material into a human body, then you need to think about how to test them in some kind of like a bioliquids. And in this study, they actually try to measure ferroelectric crystal biocompatible in the sodium chloride electrolytes. And here the insulated probe is used for enhanced resolution, and of course more important is sometimes they want to add some DC to change the environment. And this is the result that I think the paper is still under review at this moment. So you can see for this material and air in contact resonance, you can see a very clear domain. And if you use the same frequency to do the measurement in water, of course it's going to be non-resonant, non-contact resonant with the same frequency, because environment change, because your like a cantilever mechanical response change. But you still can see the domain here. But if you run the measurement in contact resonance in water, you can see more detail. Many more details with this measurement. Of course, we actually conduct a whole series of measurement, including in like 10 millimolar sodium chloride, 0.5, like 100 millimolar sodium chloride, and half molar sodium chloride. And as you can see here, right, as it's less than half molar sodium chloride, you still can see the piezo response. You can differentiate them. This meaning that okay, if it just has a electrolyte has about like 100 or 200 millimole, it's okay. I mean, this material is still functional. And we also do a lot of details with analysis that I'm not going to go to the detail here. And of course, and of course, as I mentioned in liquid, one of the advantages you can do high resolution measurement. And again, we can show that here. It's just on a high resolution imaging, you can see that both the phase or the amplitude response looks like the resolution only limited by the antip radius. And we do have some data showing that the insulated probe would behave better than the non-insulated probe. Of course, there's a lot of simulation ongoing at this moment to understand if it's really better or just for this specific case. And carbon probe for surface measurement is very popular. For surface potential measurement is very popular in the air for a lot of semiconductor devices or even corrosion research or battery research. Of course, people would love to run it in a in a liquid example. And here's actually a recent example, ACS Nano, showing that measure the surface potential in a closed environment, fully in liquid. And but there's a problem with this Kelvin probe technique, because in principle it's just not going to work for high concentration electrolyte. And then Dr. Liam Collins from Oak National Lab, he has a lot of study focused on this, and I would encourage you to take a look. So pretty much because in the polarized electrolyte concentration, the electrical double layer is going to screen any surface charge. So of course, alternatively, if you want to do a measurement, you can use a STM-based technique to do scanning electrochemical potential microscopy, which actually developed by Bruker about 10 years ago, or just use a technique that Mike just introduced. Of course, we can. Our technique use a insulated probe. We have no problem to do this kind of low concentration measurement. In this example, platinum silicon nitride, you can differentiate different potential different domain with different surface potential using just a traditional Kelvin probe technique. And actually, the more importantly is actually for the conductivity measurement, because because now you need to use DC bias. You have a high concentration electrolyte, and you have to use an insulated probe to avoid a leak, avoid the capacity charge. And I think this is an example I showed last year on another webinar, and then Mike already explained a lot of you about this kind of a mixed, very high junction systems. So, and we can see that, for example, here, this kind of like semiconductor metal junction, you show a very good diode behavior, but once you add a drop of liquid on that, you can see the IV curve totally change. So this is need to be careful that when you explain your data, when you try to infer your data measurement in air to the system in liquid, it would be better that you can conduct a measurement directly in situ, in liquid. And battery is another domain, right? So as I mentioned just now, the SEI layer or the surface layer on the cathode, or SEI layer on the anode, people would love to have like a ionical conductive, like electrical insulating or mechanical elastic robust. So a lot of interesting is how the SEI layer conductivity would affect the performance of the battery. And there's a lot of in situ measurement already showing how the SEI evolved during the voltage cycling. And this is one example published in Chemical Communication. And this is actually a cathode. And you can see that some of the site that they actually cathode, that you can see the topographic evolution. And actually, this data is actually from Professor Zhigao Huang's group, and this is very interesting, right? So this is actually in the battery's environment, and then and we do the conductivity measurement, and this is the voltage pattern they use. And before any charging, you will not see any current features or any current distribution. It's just kind of featureless. You can see a very sharp topographic feature on each particles. However, when after this kind of like a voltage cycling, you can see that first topographically the edge like smoothen out, which actually is similar to the previous example I showed. And more important, you can see that in some of the boundary, the conductivity shows up. So we're still trying to understand this data at this moment, but this is very interesting, exciting, and more important, we are showing that now we can do a conductivity measurement in a real electrolyte solution. So in conclusion, Bruker offers a set of unique solutions that enable the nanoelectrical study in liquid, and this is actually including a lot of electrical modes. And we believe that this new technique will enable a lot of new research area. So at this moment, I think both Maya and I would be happy to take any question you might have.
Very good. Thank you, Teddy. Thank you, Dr. Nellist. Thank you for sharing your research results with our audience. And Dr. Huang, thank you for showing the audience the benefits of Bruker's nanoelectrodes and new data cube modes. I know we're up against the hour here, so appreciate you staying over. But we'll take advantage of the fact that we have both Dr. Nellist and Dr. Huang. So we'll ask a few questions here that have come in. This is for Mike. What kind of light source do you use to illuminate the photoelectrode? Did you use a glass fiber or bring the light to the electrode?
Hi. Yeah, that's a good question. So you could use a glass fiber, and you probably wouldn't need to have the custom AFM setup in that sense. We have our system specifically raised 7 inches so that we could put any light source that we want underneath. So for all the experiments that I used, I simply used a 405 nanometer LED light source that I could place directly underneath. Yeah.
Very good. I'll ask a follow-up question. Is there any limitations on what wavelength light you can use for photo excitation?
I don't believe so. As far as yeah, you could use most light sources. I think if you start to approach the same wavelength as the laser that's being used to deflect off the cantilever, there might be some interference there. But otherwise, it's pretty flexible.
Very good. Let's go on to another question. And this is again for Mike. No spatial mapping of surface potentials was demonstrated with your dual working electrode technique. Would these measurements be possible?
I think they would absolutely be possible, especially with the force volume technology that Dr. Hun walked us through. And that could potentially be a promising next step for the technique.
Okay, very good. And let me go back here. This is for you, Dr. Nellist. Again, a quick question to Mike. How does this method apply to porous catalysts?
Well, so the catalysts that we were looking at were in fact porous. Since the catalysts are conductive, though, we can rest the probe directly on the surface of the catalyst and still be able to make those conductivity measurements.
Okay, very good. The current measured in cyclic voltammetry in the photoelectrodes was in the order of milliamps per centimeter squared. Do oxygen bubbles perturb the AFM measurements? Have you seen these in your experiments?
Yeah, that's also a good question. So if we were to go to really high current densities, that would be problematic. Generally, though, in the range of anywhere up to up to like maybe a milliamp per centimeter squared, we were able to successfully make the measurements. But if too much oxygen was evolving off the surface, there could be the tendency for those oxygen bubbles to push the cantilever off from the surface, and we would simply have to take the electrochemical cell off, clear off the oxygen bubbles, and just repeat the measurement.
Very good. There's another one for you, Mike. Hi, Mike. I have a question about this the semiconductor electrolyte interface during your measurements. Does the gas evolution affect your measurements?
Yeah, so I think that's in line with the previous question. So they definitely can. You just have to be a little careful about how you make them, or just ensuring that the cantilever stays in contact with the catalyst throughout the entire measurement.
Okay, very good. And this is a question for Teddy. For the data cube modes, can you hold the tip on the surface for studying some time-dependent electrical properties? And if so, how long can you hold it?
This is a good question. This is actually the point I missed. For one of the advantages that the data cube introduced. So with this data cube technique, as I mentioned, you can hold the tip on the surface, and then you don't have to ramp any electrical parameters. You just hold it there and do your measurement. And this is essentially just a time dependence measurement. And this is going to be very, very useful for a lot of has a time dependent response electrical property material. And for holding for how long, really long actually. You can hold it for hours, no problem. I think we have a ramp scripting. We have a ramp scripting function that allows you to hold the tip, and then we actually used to hold the tip on the sample surface for some electrochemical measurement that hold it for like an hour to get a CV curve or whatever we need to do for like a microstructure and then electrochemical studies.
Okay, very good. Let me go back to Mike, hi Mike. How much spatial variation did you see in the surface potential of the that COPI, or did you just hold the tip in one place? Could you please get spatial information?
Sure, yeah. So we were using relatively thick COPI catalyst layers around 100 nanometers. And so the catalyst was completely in contact. So overall, we did test at several points throughout the surface of the sample. But I think because that catalyst is so conductive, we didn't necessarily see very much variation in the potentials that we're measuring at the surface. We suspect if we go to lighter catalyst loadings or set up our samples in some way that we could isolate individual regions that are catalyst coated, that we could in fact potentially see variations across that surface. But for these measurements themselves, they were pretty consistent.
Very good. Mike, if you don't mind going back to slide 10, we'll have to give you control just for reference here on a question. Can we take control? Okay, slide 10.
Okay.
Very good. Can you explain which electrochemical technique you use to measure the applied voltage with the tip?
So with our potentiostat system, we could set up a measurement where through the second working electrode of the potentiostat, we could simply measure the open circuit potential of that second working electrode, which is going to be set at whatever, because it's in contact with that gold substrate, it's going to be measuring whatever potential we're applying through the first working electrode. So yeah, it requires 2 working electrodes from the potentiostat.
Okay, very good. Thank you for that, Mike. And this one is for Dr. Huang. Can you do data cube piezophorus microscopy in polar liquid, like in biological environments? If so, can you detect ionic transportation dynamics in membranes?
Yes, as I mentioned, right, as long as you resolve the problem with the chemical compatibility and the spilling issue, of course, I just already showed you the product we have. And then you can run any nanoelectrical mode in liquids. Of course, there's some practical concern when you run on the when you run in the power liquids. I already explained to that. But data cube nanoelectrical mode, just another AFM mode. And so so there's no problem to run this kind of like a conductivity measurement, or if you want to use if you want to send a sample bias or tip bias to drive the ion in and out from a membrane or from like a battery material, and look at the mechanical or the volume change of the sample. Yes, it's definitely doable, because it just send an AC drive and then see the AC vibration of the volume, and then you can understand the ionic dynamics. So yeah, this is very promising technique that I believe it's going to be very useful for this research area.
Another question for Dr. Huang. How do you save the working integrity of the AFM while using polar liquids for conductive AFM?
Say again?
How do you save the working integrity of the AFM while using polar liquids for conductive AFM? I would imagine that's the integrity of the tip.
So I actually have quite some slides for my last webinar showing some control experiment though. So we have done this manual, of course, according to requests from different professors. They have different application need. At the beginning, we show the measurement just in pure water, and later on, this battery folk would like to run in a high electrolyte concentration. We also have a lot of dirt on that. And later on, people want to measure in a high bias. So we actually had to do some conductivity like a higher like 2 or 3 volt, and the tip is still intact. So the tip itself is very robust. So, and of course this is because we actually spent like years on figure out how to coat the tip like robustly. And this actually, I think Mike also has used this probe for a year. He also has some idea about how robust this kind of tip on the electrochemical environment. So I'm not sure I answered the question, but all I can say is the probe is very robust in electrochemical environment.
Very good. Thank you, Dr. Huang. This is for Dr. Nellist. In your latest article about potential sensing electrochemical AFM, it was written that for potential sensing dual working electrode measurements, the counter-electrode potential sense probe was separated from the counter-electrode and attached to the AFM tip. Can you explain how that was done?
Sure. So yeah, this will also elaborate on the last question that was asked. So for these measurements, our potentiostats that we use are biologic. And so for the counter electrodes, there's 2 components to the counter electrode, one that allows the current to pass through, and then the other one that essentially just senses potentials via the counter electrode. So one feature of the biologics are that you can separate those 2 components of the counter electrode and use that potential sensing component to sense the potential elsewhere in the system. So we technically didn't have a traditional bipotentiostat setup. We were really only using one of the channels, but we're able to separate that so that it could instead be sensing the potential via the surface of the probe. We also were using an ultra-low current cable that gave us the extra, or we believe at least gave us the extra resolution for the potential sensing that enabled us to make these sensitive measurements.
Very good. And just respecting everybody's time here, I'm going to take one more question, and we have many others that we'll make sure that we answer to you via email. But again, this is in particular to slide 10 again. In order to measure the OCP of the tip, do you have to measure AFM in contact mode or in peak force tapping that you make the same measurement?
Yes, that's also a good question. I didn't clearly specify that. We can scan the surface while being in the peak force tapping mode, but then we can use the point and shoot functionality from that the images that we're collecting from the peak force tapping to select the particular region that we want to probe, and then using the point and shoot rest the probe on the surface for the extent of the electrical measurement that we make.
Very good. I want to thank you both Dr. Nellist and Dr. Huang and our audience. Thank you for staying over. We appreciate that. As mentioned previously, this will be recorded and a link will be forwarded to you if you are an attendee. I encourage you to forward the link to your colleagues and friends if they're interested in this technology and this type of research. Again, thank you for reaching out and listening to Bruker and Michael Nellist. And again, Dr. Nellist, congratulations.